Right now, the sun is firing 1 million tons of superheated plasma at Earth every single second. Most of the time, our magnetic field quietly deflects it. But occasionally, the sun erupts with something far more violent, a solar flare. When a big one hits, it can knock out satellites, fry power grids, and light the sky with the most spectacular auroras on Earth. I'm Mr. Sticklab. Today we'll find out what causes a solar flare, what happens when it reaches Earth, and why scientists watch the sun so carefully. It starts with understanding what the sun actually is. The sun isn't a solid ball. It's an enormous sphere of plasma, gas so hot that electrons are stripped from their atoms, turning the whole thing into a roiling sea of charged particles. Deep in the core, hydrogen atoms are crushed together under immense pressure and fused into helium, releasing staggering amounts of energy. That energy claws its way outward through two zones. In the radiative zone, it bounces around for thousands of years. Then, in the convective zone, giant columns of hot plasma rise to the surface, release their heat, and sink back down. And it's this constant churning of charged plasma that creates something extraordinary. Because when charged particles move, they generate a magnetic field. Loops of magnetic force arc out from the sun's surface, especially around its equator. As the plasma churns and twists beneath the surface, these loops get tangled, wound tighter and tighter, and stress builds like a coiled spring, until something snaps. The field lines suddenly reconnect, jumping to a new, lower energy shape, and releasing all that stored energy in a single violent burst. That burst is a solar flare. In a fraction of a second, energy equivalent to billions of nuclear bombs erupts as a flash of intense light and radiation. At the same time, the blast hurls a giant cloud of magnetized plasma into space. This is a coronal mass ejection, billions of tons of material, racing outward at up to 3,000 kilometers per second. Flares are ranked by strength. A B and C class are mild. M class can cause brief radio blackouts, but the giants are X class, and the strongest ever measured was an X-28, so powerful it went off the scale. In September 1859, an astronomer named Richard Carrington was sketching sunspots when he saw something no one ever had: a brilliant white flash erupting from the sun's surface. 18 hours later, the CME slammed into Earth. Telegraph systems short-circuited across the world. Sparks leapt from the wires, and paper caught fire in telegraph offices. Auroras lit the sky as far south as Cuba and Hawaii. It became known as the Carrington Event, still the most powerful solar storm in recorded history. If one struck today, with our world built on satellites, GPS, and connected power grids, the damage could run into the trillions. But most of the time, Earth is protected. Our planet's magnetic field acts as a giant invisible shield, deflecting the solar wind around us. When a storm does arrive, those particles are funneled along the field lines toward the poles, where they crash into gas high in the atmosphere and make it glow. The colors depend on the gas and the altitude. Oxygen glows green lower down and red up high. Nitrogen adds blue and purple. Every solar storm paints a slightly different sky. So a solar flare begins in the sun's tangled magnetic field. Plasma loops build stress until they snap, releasing enormous energy and hurling a coronal mass ejection into space. When one reaches Earth, our magnetic field deflects most of it, but extreme events can overwhelm our technology. That's what a solar flare is. I'm Mr. Sticklab. The sun is 93 million miles away, but it's still very much in charge. Stay curious, and I'll see you in the next one.